Alright, hello everyone and welcome to Lab 5 of our Organic Chemistry series that is online this semester, and this week we're going to be going over thin layer chromatography. So chromatography is the operative word here. That's the technique we're going to be analyzing, and the purpose of today's experiment is to use this technique to identify the components of an unknown mixture. But before we can fulfill this purpose, we have to go over what chromatography is. So the word chromatography means it refers to a technique which separates compounds based on their polarity. So the previous experiments we've been dealing with all the different separation methods, and this one deals directly with polarity of the molecules that are going to be separated. The term chromatography comes from the Greek, so chroma in Greek means color, and graphia in Latin meaning to write. So roughly speaking, the term chromatography means to write with color, or color writing, and you'll see in one of our experiments why that is. Now, the applications of thin layer chromatography, or chromatography in general, are theoretically limitless. This is perhaps the most powerful technique that you'll learn this semester in lab, merely because of how many applications it has. So in pharmaceuticals, for the developing of medicines, they use it in agriculture to test for pesticides, and forensic science to check for explosives residue or inks and pens. The applications are really endless with chromatography. So let's talk about the three elements of chromatography, and these are going to be found no matter what type of chromatography you're doing. In this case it's called thin layer, but these apply to all forms of chromatography. So the first element is a mixture, and this mixture contains components which are to be separated, and this mixture is often called the analyte because it's often being analyzed. The stationary phase, which is a solid that will interact with the mixture's components via intermolecular forces. So these are non-covalent forces. They're the forces which attract molecules together, and those are what is going to be separating the molecules in our mixture. Now, the last component is called the mobile phase, and as the name implies, it's a liquid solvent that moves, and it will push, quote unquote, push the components through or along the stationary phase. So there's three components. We have a mixture which is going to be separated, we have a mobile phase which pushes the mixture, and a stationary phase which, because of its interactions, will separate the components of that mixture. Now, if that sounds a little abstract, we've created this little example to help us explain this phenomenon. And let's talk about the polarity aspect. So as I mentioned, chromatography is dealing with the separation of molecules based on their polarity. And I have this table here which describes the differences between polar molecules and non-polar molecules in chromatography. So if we have a polar molecule, as we went over in previous labs, the OH, these molecules have more OH, NH groups and dipoles. So these are the functional groups that have polar functional groups and make them more hydrophilic. They're more water-loving. In contrast, a nonpolar compound will have fewer of these polar functional groups, so less OH, NH, and dipoles. Now, as far as these go, in chromatography, we have this little diagram here. So here we have a stationary phase, which is comprised mainly of silica gel. So silica gel is basically silicon dioxide, which is essentially purified sand, and it has a very high surface area. And to zoom in on the surface area, we have all these silicon OH bonds. So these are referred to as silanol groups. And these groups are very, very polar. So they're water-loving. So if you have a polar molecule will interact with this phase, stationary phase, much more strongly than a nonpolar molecule. And as it's being pushed along by an organic solvent, it's going to move at a slower pace, whereas a nonpolar compound will move through the stationary phase at a faster rate. And to demonstrate that, let's, for example, place two molecules. Say we have a mixture of a polar molecule and a nonpolar molecule, and we introduce that to our stationary phase, and we push it along using our organic solvent, our mobile phase. What will happen is that the nonpolar molecule will be less attracted to the stationary phase and will be moving at a faster rate, whereas the polar molecule really likes to stick to the stationary phase, so it's going to move at a much slower rate. And eventually, if you were to take a snapshot of this mixture or of this experiment, you would see that the nonpolar molecule has moved farther away from the polar molecule. So this is a little abstract, so let's do an example. Let's say we have benzoic acid and benzaldehyde. So they both have a benzene ring, the difference being one has a carboxylic acid functional group and the other has an aldehyde functional group. Now remember, a polar compound will have more OH and NH groups and dipoles. Now both of them have a carbonyl, so this C double bonded to an O. So that's the same, but the difference is that the benzoic acid has an OH, and that makes this molecule much more polar than the benzaldehyde. And if you remember how hydrogen bonds work, really this H can form a hydrogen bond with the OH on these silanol groups, whereas this benzaldehyde cannot. So what will end up happening is the benzaldehyde molecule is attracted to these OH groups much more strongly and will want to stick to it much more readily than the benzaldehyde. And eventually the benzaldehyde will move faster and faster, whereas the benzoic acid will be constantly tugging on these OH groups and they'll separate. So now let's cover an example that we did previously. If you remember in lab 2, we were making acid analyde, this molecule, and we were making it from aniline. So say for example we were to analyze a mixture which contained both of these compounds. Well, how would those separate? Well, in order to do that we have to look at again at their intermolecular forces. So aniline has hydrogen bonding from these NH bonds, but so does acid analyde. Now the difference is that acid analyde, in addition to having hydrogen bonding because it has an NH bond, it also has this dipole here because of the carbonyl group, the C double bonded to oxygen, and that makes the acid analyde molecule much more polar than the aniline. So if we were to introduce these two as a mixture, as our analyte, onto the stationary phase, we would see that the acid analyde would stick to the silica gel much more frequently than the aniline, so the aniline would move at a faster rate. So the nonpolar molecule moves faster, whereas the polar molecule moves slower. Oops, flip that over there. Now, if this is a little abstract right now, even with this demonstration, don't worry. I think after seeing the experiment, you can see how this technique works more tangibly. Now, we were talking about a stationary phase, and that stationary phase, let me bring this back for a moment here, is silica gel. Now, obviously, this doesn't exist in a vacuum. We have to create something that we can put this silica gel on. Now, in the case of thin layer chromatography, if we have a thin layer of this substance and we coat it onto a plate like this, so you can see this is a glass plate, sometimes they're made of aluminum, but this one happens to be glass, and we smear a thin layer of this silica gel. You can see that you can even scrape some off if I etch it with my nail, perhaps a little bit. Yep. If we have a thin layer of it, it's referred to as thin layer chromatography. So if I were to apply a mixture to this TLC plate and tap it here, and if I take this mixture and I stick it in a beaker, so this plate here represents the TLC plate, and this beaker has some sort of solvent, which is our mobile phase, what will happen is that the mobile phase, let's mark it here, the mobile phase will be whipped up the plate via capillary action, and it will move this mixture up the plate. And that's what this diagram symbolizes. So I have my mixture, I place it into a sealed chamber with the mobile phase in it, and this is our stationary phase. And we develop the plate, and we see that our mixture has two components in it, a red spot and a blue spot. Now, in order to quantify, the relative rates at which they move, we can calculate what's called the retention factor, so RF. And the RF is an equation which describes how fast these molecules move throughout the stationary phase. And the equation is the distance traveled by the spot divided by the distance traveled by the solvent. So eventually, once the solvent makes it all the way up to the top of the plate, you'll mark it with a pencil, and this is what this line symbolizes right here. So this is the solvent front. Okay, and then we have this starting point here, and by the way, the starting point on the TLC plate, this is referred to as the origin. Now, in order to calculate the lengths, we would just take this distance, so we have this distance here for the blue, we have this distance here for the red spot, and then we have this distance here for the solvent front. So let's say, for example, that the solvent front here, this distance, let's just say it's 4 centimeters. Let's say that this red spot moved 3 centimeters, and let's say that the blue spot moved 2 centimeters. So in this theoretical example, let's figure out what the RF of each component is. So the RF for the red spot, so I'll write it in red, the RF here, would be equal to the distance traveled by the spot, which is 3 centimeters, 3 centimeters, divided by the distance traveled by the solvent, which is 4 centimeters. So 3 divided by 4 is 0.75, and that's the RF. And notice it's a unitless value because the units cancel out, and the RF will never be greater than 1. It's some value between 0 and 1, but it can never be greater than 1 because the spots will not move farther than the solvent. And for the blue spot, we can do the same calculation. It's a very simple calculation. 2 centimeters divided by 4 centimeters, and obviously this value is 0.5. So those are our two RF values. And you'll notice the more polar molecule, remember B in this case, the blue spot is the more polar molecule, is more strongly attracted to the plate, so it's going to have a lower RF and it's going to move a shorter distance compared to the red spot, which is less polar, and it moves a farther distance. So let's finally compare. So we've discussed the TLC plate and the RF. Finally, the last thing I wanted to discuss is the mobile phase. So the mobile phase is an organic solvent, typically, and it consists of a mixture of one polar solvent, which is typically ethyl acetate, and one non-polar solvent, which is typically hexane. And you can adjust the polarity of this mixture by changing the ratio of ethyl acetate and hexane. So the more ethyl acetate there is, the more polar the mobile phase is, whereas the more hexane there is, the more non-polar the solvent is. Now, if our mobile phase is more polar, in other words, it has more ethyl acetate, then all the spots will have a faster / higher, will move at a faster rate, and they will have higher RFs. Now, conversely, if we have a mobile phase which is less polar, then all the spots will move at a slower rate, and they will have lower RFs. So let's compare this little example here. Say we take our same TLC plate from the previous example, and we develop it in a mixture of 1 part ethyl acetate to 9 parts hexane. So this is a very non-polar mixture. We develop the plate and we can see that the spots are not very separate and they have very low RFs. They're very close to the origin. So this is not ideal. Now, if we take the same plate and we develop it in 50-50, so this is 1-to-1 ethyl acetate to hexane, we have good separation. So this is like our previous example, and these spots are well separated and they're in the middle of the plate. So this is the ideal sort of a target when you run a TLC. Now, if you have the opposite, in which case you have 9 parts ethyl acetate and 1 part hexane, which is a very polar mobile phase, the spots will be pushed very quickly up the plate, and once again you have less separation. Now, you really want the greatest separation between the spots, and that's achieved by having some mobile phase that is not too polar but not too non-polar, so somewhere in between. So thank you all for watching, and we'll see you in the experimental. Alright, hello everyone, and welcome to the experimental section for thin layer chromatography. So this right here is a TLC plate, as I showed in the video. It's a glass-backed plate and has a thin layer of silica gel, which is our polar stationary phase. So to perform a thin layer chromatography, you take your plate, and the first step is to mark the bottom of the plate about 1 centimeter from the bottom. So we're creating our origin line here. And we're also going to mark where we're going to apply our spot. So in this case, we're only going to be doing one analysis on this particular plate. And the analysis we're going to do is dealing with a colored mixture. So what I did was I went outside, I grabbed a leaf from the tree outside, and I ground it up in this mortar and pestle. And then I extracted the this basically mash here with some acetone, and now I have a leaf extract. So as you can see, it's nice and green from the chlorophyll, and we can do a TLC. Now this is interesting because the person who invented chromatography was originally separating pigments from leaves, so this is sort of like recreating the discovery of chromatography. So what we can do is we have our mixture, our analyte, to be separated, and we somehow need to apply it to our plate. So obviously we can't just pour it onto the plate because that would be way too much sample. So in order to do that, we need to take a capillary tube, which are these glass tubes, and what you can do is you can take this thin glass tube and dip it, if I can grab one, dip it into the mixture here, and then you take the capillary tube and then you spot it onto the plate. Now these are a little fragile and I always tend to break them. So instead, I'm going to use a very thin needle, which I have cut the tip off of. So this is referred to as a spotter. So some spotters are metal like this one, but you can also use glass spotters. So what we do is we take our capillary tube, or our spotter in this case, and we just dip it, and naturally, because of capillary action, the mixture will rise up into the tube. And this is the challenging part. It takes some getting used to, but you immobilize the plate and you very gently tap it. So tap. So you can see that there's some liquid being deposited onto the origin. Now, for a normal TLC, that would be sufficient. You don't want to apply too much compound. But in this case, because it's a very beautiful experiment, I think I will apply a nice band across the origin so you can see a nice separation. Okay, so now that I've applied my sample, what I want to do first is clean this, because I'm going to reuse it. So I'll dip it into some acetone to clean it, and I'll just kind of deposit it onto a paper towel that I have on the side. So take some. In fact, you can just do it on this paper here too. Just kind of rinse it out, make sure there's no residue, so the next time we use it, we don't contaminate the next sample. Do that a couple of times. Okay. We'll place that off to the side. So now that we have our plate, which we have created, we've applied our sample. Now we're going to place it into our developing chamber. So our developing chamber is right here. So this is one of the purpose-built TLC chambers, which is meant for doing it, but you could do it in a beaker, which is much cheaper. This runs about $200. So what you do is you fill this up with a few millimeters of your mobile phase, and then you stick your plate into here, and then you cover the top, and then it'll take a few minutes for the solvent to run up the plate. So let's go see what that looks like. So we've got our TLC chamber here. I'm going to place some solvent into there, so you don't want to put too much. This is a interesting mixture. It's made to separate the pigments and leaves, so what exactly it is not too much of concern. There's actually 5 different solvents in here. Now, when you develop your plate, it's important that the level of the solvent here does not exceed the level of the origin here, because if this solvent is higher than this origin, the sample will simply dissolve into the mixture, into the chamber, which is what you don't want. So now that we've got our mixture here prepared, and we've got our TLC plate prepared, we can deposit it into the chamber with a pair of tweezers. So let's see if I can do it. There we go. Okay, and now we can cap it and simply wait for things to separate. Alright, so it's been a few minutes and our TLC plate is almost done. The solvent front is almost at the top. So now is a good time to take it out. But before we take it out, it's important that once we take it out, we immediately mark the solvent front, because the solvent will begin to evaporate. So the portion of the plate that is dark and gray indicates where the solvent has traveled. And since the solvent will evaporate once we take it out of the chamber, we can't wait for it to evaporate. We need to do it immediately. So let's quickly take that off and mark about where the solvent ended. And it's not a super exact science. So now what we can do is we can shake the plate a little bit, maybe let it evaporate. Okay, and now as you can see on our plate, we have some very good separation. Well, not very good, but some decent separation of all the compounds. Now it's interesting because leaves contain a lot of natural products, as we discussed in the previous lab. Now the top portion, this is very interesting because the top spot is actually beta carotene, which is the pigment that you find in carrots, hence the word carotene. And down here, the green spots and the yellow spots pertain to chlorophyll in their different forms. So chlorophyll is obviously the portion of the leaf that allows the plant to perform photosynthesis. So that's how plants get their energy, and we can see separate those components based on here. Now you'll notice beta carotene is almost at the solvent front. It has a very high RF, and that's because beta carotene has no polar functional groups. It's pretty much all carbon and hydrogen. So there's no oxygen, nitrogen, or oxygen, hydrogen, and nitrogen, hydrogen bonds. So it'll be right at the solvent front. So this kind of displays the color writing aspect of chromatography, so it's kind of like separating the colors. Now, an issue arises when you want to separate compounds that are colorless. So in our next example, let's get another TLC plate, and this time instead of spotting one compound, we're going to spot two compounds. So I'm going to create my origin as before, try to keep it straight. Okay, and it's important that you use a pencil when you mark the TLC plate. First of all, pencils mark it very well, but if you use a pen, sometimes the ink will actually separate on the plate, so you don't want that. The graphite in the pencil is what works best. So in this example, I'm going to run two spots. In one of them, we're going to do benzaldehyde, so we'll see B is for benzaldehyde, and then on the rightmost spot, we'll do benzoic acid. So conveniently, I have some samples made up of those. So where's our benzaldehyde? Yep, here we go. So our benzaldehyde sample is here. So we can take our spotter as before and spot the plate. So get all the acetone out of it. And this time, because it's not colored, we'll just give a few spots. Okay, cap that. Now we'll take our benzoic acid. Okay, so here's our benzoic acid solution. And you want to try to keep the spots small because it ensures that there's good separation between the components. If the spot is very large and diffuse, sometimes the spots can overlap. Okay, that should be good. Then we'll clean out our spotter. Okay, so now we have our prepared TLC plate. We can put it into the chamber. Alright, so we've got our TLC plate here, which is prepared, and we've changed the mobile phase. So we've changed the mobile phase from the previous solvent, and now we're using 20% ethyl acetate and hexane. So we can take our plate, and we can use our tweezers to place it into the chamber. Cover it and wait a few minutes. So it looks like our TLC plate is done, so we'll extract it from the chamber. Okay, and mark the solvent front. Okay, and because these two compounds unfortunately are very colorless, we can't really tell what it looks like because it's not colored like the pigments in a leaf. So to solve this problem, we can examine this TLC plate underneath a UV lamp. Alright, so we've got our benzaldehyde and benzoic acid TLC plate here, and obviously since the compounds are colorless, we can't look at it with our naked eye. So in order to facilitate viewing the plate, we're going to use this right here, which is our UV lamp, and the UV lamp will emit UV light at 254 nanometers, and basically these plates are coated in a phosphorescent material that will appear green. But if there is an organic compound that absorbs UV light, then it will block the green from showing. So it kind of looks like purple spots on a green background, and that'll tell us where the organic spots are located. So to do this, we can turn off the light. There we go. And it's also very important to not look directly into the UV light. This is kind of easy because this lamp is fairly immobile, but if some UV lamps are portable and you don't want to shoot it into your eye because the UV light is actually mutagenic, so what we can do is we can turn on the UV light. So as you can see, there's actually some TLC, there's some stationary phase that's fluorescing here from just using this TLC station over. So we can take our plate and we can place it underneath the UV lamp, and as you can see, there we go. So on our left lane here, we have benzaldehyde, and then on the right lane, we have benzoic acid. Now, you'll notice that the benzaldehyde lane actually has a couple spots. It has a major spot up here, it has a smaller spot here and here, and that's because this benzaldehyde is kind of old, so there are some impurities. So for our purpose, we're kind of going to neglect these spots, just imagine they weren't there. This is the benzaldehyde major spot. So what we can do is we can trace the outline of the spot with a pencil, and you'll notice for the benzoic acid, it's not so much a spot so much as it is a streak. And that is kind of along the lines of what we predicted, right? Benzoic acid has a very polar functional group, a carboxylic acid, and because it loves the stationary phase so much, it's actually streaking along the plate instead of being pushed along in a solid dot. So that's the result here. So we've circled our spots, and they coincide to what we predicted in the pre-lab. So the benzaldehyde, because it has a less polar functional group, has a higher RF than the benzoic acid, which has a lower RF. Okay, so now we're going to do a TLC on our acid analyte product. So we'll prepare the plate in the same way. So on the left spot, I'm going to put aniline, so I'll just write that A for aniline, and then for the acid analyte, put AC. So I have an aniline sample here, so we can spot that onto the TLC plate. Clean our spotter. And now we can get our acid analyte sample. So we've taken a crystal of our acid analyte from the second week of lab, and we can spot it onto our plate for analysis. So take a little bit and spot the plate. Okay, and we're going to lower this into the chamber with the same solvent system, so 20% ethyl acetate in hexane. Alright, so our aniline acid analyte plate is just about done. Okay, we can pull it out and mark the solvent front and then take it to the UV lamp. Okay, so here we have our aniline and acid analyte TLC plate, and on the left lane is our aniline and on the right lane is our acid analyte, and here it's a much nicer looking plate. There's no impurities in either sample. In fact, this proves that our sample from the acid analyte synthesis is fairly pure. So if you remember, we had a very good melting point, which was very close to the literature reported value. And this TLC plate also tells us that our acid analyte is pretty much free of any organic impurities. So if there's only one spot in your sample, that kind of tells you that your mixture is fairly pure. There's nothing else in it. And as you can see, as we predicted, the aniline, which has hydrogen bonding, is a bit higher, but because the acid analyte has hydrogen bonding in addition to a dipole from the carbonyl, the acid analyte is more polar and has a lower RF compared to the aniline, which is a little less polar, so it has a higher RF. So this is looking like a good plate. Alright, so let's flip this plate around. We've done our TLC of the benzoic acid and the benzaldehyde, and we've also done our TLC of the aniline and the acid analyte. So the final plate we're going to run in today's experiment is an unknown. So the purpose of the unknown is to figure out what components are in the unknown based on the TLC results. So in order to do this example, what we need to do is we'll start our TLC plate by marking the origin once again, but instead of running 2 lanes or 1 lane, we're actually going to have 5 lanes. So the unknown could have any combination of acid analyte, aniline, benzoic acid, and benzaldehyde. So we don't know which of the 4 it has and how many of each it has. So we need to run all 4 next to the unknown to figure out what is in the unknown. And the way we can tell is that if it has a certain compound in it, in the unknown, it'll have the same RF value. So the spot will be at the same distance, and you'll know, oh, it has this inside of it. So let's see if we can fit 5 spots onto our plate here. Okay, looks pretty good. And we can label them. So why don't we do our benzaldehyde here, our benzoic acid, okay, our aniline, and then our acid analyte. And then our unknown will be the rightmost lane. So there's 5 lanes. So our unknown and then 4 references or 4 standards which we're going to compare it to. So now we can just spot them all into the plate. Okay, so we've got our TLC plate, which has our 4 reference compounds and our unknown. And now we're going to put it into the chamber. Okay, so we're going to place it into our chamber with our tweezers, just as before. Alright, so our unknown TLC plate is done, so let's retrieve it from our chamber. Okay, mark the solvent front, and then we'll go look at it under the UV light. Okay, so this is our most challenging plate here. This is our plate with our 4 reference standards and our unknown sample. So just going from left to right, this left lane, remember, is the benzaldehyde, so it has these 2 impurities, which are not a big deal. The main thing is that the benzaldehyde spot is right here. Then we have our benzoic acid, which remember streaks on the plate. And then we have our aniline, which is showing up here, and the middle lane. Now on this lane is the acid analyte spot. And then here, or the rightmost lane, is our unknown sample. So it's up to you guys to use this TLC plate to figure out what components are in the unknown sample. So compare the RFs, see at what distance the spots are, and use the 4 reference standards to determine that.